Okay, so what is the concept of the growth of functions, and why do we need this to study the performance of algorithms? Let's start with some definitions, and I believe it's going to become more clear as we proceed why we base the mathematical background of analysis of algorithms on the growth of functions. Suppose we have two functions f and g on the set R, the real numbers. We say that f of x is a big O g of x if for all x values greater than some k value, the absolute value of the function f is less than or equal to some constant c times absolute value of g of x. So this means f of x in magnitude stays below some multiple of the absolute value of g of x when x exceeds some value. If it is the other way around, f of x called a big omega of g of x, if for all x greater than some k value, f of x in magnitude is greater than or equal to some constant c times the magnitude of g of x. Now, this we can actually visualize something like this. Let's say you have two functions f and g. Now, let's say initially they might be occasionally one of them is larger, occasionally the other is larger, or maybe I should use a different color here. Okay, so something like this. Okay, it doesn't really look as intended, and maybe, yeah. Okay, so the blue one, after some point, it stays above. Let's say this is the value, say this is k, okay. Um, well, this should indicate some constant c times, let's say, g of x, and the red one is f of x. In this case, we say that f of x is a big O g of x. So essentially what this means is the function g, as x gets larger and larger, grows faster. Okay, essentially these two functions are increasing or growing functions in a general sense, let's say, towards infinity. But g of x in this example, it grows faster. It approaches infinity in faster than f of x. So we are talking about not specific values of the functions, but about their rates of growth. So this is the terminology. If f of x is big O of g of x, this means f of x grows slower than g of x after some threshold, k here. So it doesn't really matter which one is greater below that threshold, but there is some threshold beyond which this behavior is settled. This race, let's say, is decided, and one of the functions have won. Okay, or if it is the other way around, for instance, f of x grows slower. In this case, we say that g of x is big omega of f of x. And if both of them are satisfied together, if f of x is both big O g of x and big omega g of x, then we say that it's big theta of g of x. Now, at first, this could feel counterintuitive. Now, when you say f of x is big O g of x, you are saying that g of x is growing faster. But you also say it's f of x is big omega g of x, in which case you are saying f of x is growing faster. But essentially, if you have them both, recall the constant here, because this could be less than 1, it could be greater than 1, doesn't really matter, but you have a fixed c value. This means you have a certain range with respect to g of x. So essentially, as x grows, f of x in magnitude stays between, let's say, c1 of g of x and also c2 of g of x. So it stays in a range determined by the function g. And in this case, we see that we say that the functions f of x and g of x are of the same order. So they grow in similar rates. Their exact values are not of concern here. In this theory, we are only interested in the type of behavior they present when their inputs gets larger and larger. Let's look at a simple example right away. Let's say f of x is x squared plus 2x plus 1. Now, when x exceeds 1, we know that x squared will be greater than x, and x squared is also going to be greater than 1. So if I replace this x by x squared and this 1 by x squared, my function will be definitely greater. So for x greater than 1, x squared plus 2x plus 1 is always less than x squared plus 2x squared plus x squared. So in total, 4x squared. And now this holds for x greater than 1, and you see this 4 here serves as the constant c. Okay, so this satisfies the definition. Therefore, we say that f of x, this function, x squared plus 2x plus 1, is big O x squared. Now, you see, x squared plus 2x plus 1 is, in fact, greater than, precisely greater than x squared. But you see, with respect to growth, we can find a threshold k, which is 1, and a constant c, which is 4 in this case, so that c times x squared stays always above f, beyond the threshold 1. So in this case, we say that f of x is big O x squared. Now, with respect to notation, we say usually f of x is big O g of x, but sometimes we write f of x equals big O g of x. This is a very widespread notation. It's a little bit ambiguous because it's not really equality in the sense that we know it. So sometimes this is considered abuse of notation, and some people prefer to use an element of notation. F of x is an element of big O g of x. In this case, they treat big O g of x as a set of functions that have at least the same growth rate of f of x. Now, obviously, also, if f of x is big O g of x, this should go the other way around. G of x, in this case, is going to be big omega f of x.